Binomial literally means two numbers. A binomial expression is an algebraic expression with two terms, something plus something. The typical one would be 1 plus x. You can have any two terms added together and they would constitute a binomial expression. When we look at binomial expansion, we're interested in what happens when you take a binomial term and you raise it to some sort of power. 3 minus 7x, all in a bracket raised to the power of 15, for instance. But we're going to come at this topic from a couple of different directions. We're going to start out with some probability, and we're going to see how somehow behind the scenes the probability questions that we're asking and the sorts of answers we get connect to the results we get when we try expanding binomial algebraic terms. So let's have a go at a probability question to start with. We start off with a minor dilemma. There's one sweet left and there are two children, and this particular sweet is indivisible. It's not easy to split it or to share it. So the usual technique is to flip a coin, but what if mum, dad and auntie all would like to have a chance of winning the final sweet? It's lockdown, no one can go shopping, there's one sweet left in the house, and we all want a shot at the sweet. So how about this? I'm going to flip 4 coins and I will count how many tails we get. If you think about it, we could have anything from no tails at all to 4 tails. So we assign everybody a number. If there are no tails, mum wins, 1 tail, auntie wins, and so on. So everybody's got a number. So far, so good. However, if you look into this a little more closely, you might find there's a little bit of unfairness in here. See if you can calculate how likely it is that either mum or daughter wins the sweet, and then see what you notice. Pause the video and do some calculations with this. Think through it carefully. Think about what you already know about probability that can help you with this particular question. Okay. Hopefully what you found is you got a number that wasn't just 2/5. It's not a 1 in 5 chance that we get no tails and a 1 in 5 chance that we get 4 tails. It's actually a lot lower than that. Mum and daughter are getting a pretty raw deal. And it turns out dad's getting a pretty sweet deal with this particular one. 2 tails is definitely the one to go for if you have a choice. But the question is, why? A good way to think about this is to imagine you are one of these 5 people and you're waiting for the coin flips to be revealed. And they're going to be revealed one by one. So the first coin is thrown and we look at whether it's heads or tails. Think about whether or not you care. If you're mum or if you're the daughter, then it matters absolutely, because if it comes up tails, then mum immediately has no chance of winning. And on the flip side, if it comes up heads, the daughter immediately has no chance of winning. But auntie, dad and the son, they don't care either way. I mean, perhaps if you're hoping for 3 tails, you'd quite like the first coin flip to be tails. But it doesn't matter if it's heads, because you can still get 3 tails from the others being tails. For dad, it really makes no difference. It can be whatever. Now, this is the complete list of all the possible outcomes. And now perhaps we can see more clearly why it's not just a 1 in 5 chance for every single person. It turns out there are lots of different possibilities for some combinations. This is what happens when you color code them according to how many tails appear. So we can see that mum only wins if every single coin flip goes her way. Auntie wins with 1 tail, which could be the very last coin flipped, or it might be the 3rd or the 2nd or possibly just the 1st. But either way, there are 4 different ways that can happen, which makes it 4 times more likely that she wins. Dad has got the sweetest deal. There are 6 different ways that dad can win, because there are 6 different ways to get 2 heads and 2 tails. If you think about this from the perspective of what do we need the first coin flip to be, the answer is we don't care at all. It could be a head or a tail. And even after the first coin flip, although I have a preference, it's not essential that it comes up anything at all. 2 heads, I can still win. I just need the last 2 to be tails. 2 tails, I can still win. I just need the last 2 to be heads. A head and a tail in either order, I can still win. I just need a head and a tail in either order for my last 2. So I've got lots of outs, lots of different ways I can win. Here we're going to have a quick look at a visual representation of all the different ways we can get each of the possible outcomes. So this has just been coded up using Python and the turtle module. We're sending a bunch of turtles randomly along a path. So each time a turtle is released, they basically follow a 50-50 chance whenever they get to a choice, just as if they're flipping a coin 4 times. If they get tails every time, they end up at 4 tails. And if they get heads every time, they end up at 0 tails. But depending on what else they get in the middle, they might end up at any one of those other places. So I'd like you to think about how many different ways there are for the turtle to end up in the middle spot for 2 tails. There's multiple different routes. Think about the number of journeys that can get you there. And importantly, think about how those journeys link to the question we had before in terms of how we can count and therefore calculate probabilities. If we're going to work out the probability of each of these, the probability of no tails, 1 tail, 2 tails, 3 tails, 4 tails, then it's going to be helpful to look at how many ways there are to get to not just the final points on this diagram, but all the intermediate points as well. So for instance, there is only one way to end up with 1 tail after a single coin toss. And similarly, there's only one way to reach this particular point on the diagram. You have to have your first coin toss be heads to get there. Now, of course, there's also just one way to get 2 tails in 2 coin flips. And there's one way to get 2 heads in 2 coin flips. But interestingly, there are 2 ways to get 1 head and 1 tail. Because, of course, you could get tails first and then heads, or heads first and then tails. And that's why with 4 coin flips, there's a 1 in 4 chance of getting 2 tails, a 1 in 4 chance of getting no tails, 2 heads, but there's a 2 in 4 chance of getting 1 head and 1 tail, because it could be tail then head, or it could be head then tail. They're the 2 different ways you can do this. Now, we can go further than that. We can look at how many ways there are to get 3 tails when you toss a coin 3 times, and of course there's only one way to do that. There's only one way to do the exact opposite, but there are 3 ways to get 2 tails and a head, because they don't have to be 2 tails and then a head. It could be a head and then 2 tails. It could be a head, then a tail, then a head. So we've got 3 different ways through. But you can see that if you're going to end up at that spot with the 3 different possibilities, it comes directly from either 2 tails in 2 coin flips or a tail and a head in 2 coin flips. But tail and a head can come in 2 different ways. So really, each of these numbers can be generated from the previous pair of numbers. There is, of course, also 3 ways of getting 1 tail and 2 heads. You would need to either get a tail followed by 2 heads, or get a head followed by a tail and a head in either order. So there's lots of different combinations, but each of them follows from the ones before. The last line we can calculate in the same way. 4 ways of getting 3 tails in 4 coin flips, 4 ways of getting 1 tail in 4 coin flips, and 6 ways of getting 2 tails in 4 coin flips. You can try drawing out all the different variations. They're basically ways of getting from the very bottom corner to the top middle corner, and they follow that sort of rhombus shape in here, all the way through the middle. Each number is the sum of the 2 just below on either side. So again, you can compare with these. You can see the 6 in the middle. Those are all the versions that have got 2 heads and 2 tails. There's 4 that have 3 heads and a tail, and of course by symmetry there's 4 that have 3 tails and a head, and then there's only 1 with no heads and only 1 with no tails. So the probabilities come out like this. Of the 16 possibilities altogether, only 1 of them has no tails, 4 have 1, 6 have 2, 4 have 3, and 1 has 4. So it's not exactly the fairest way to decide who gets a sweet between 5 people, but you can see how those numbers favor the middle values. This is one way of seeing why, if you flip a coin 100 times, getting something close to 50 tails and 50 heads is the most likely result. It's much, much more common to be somewhere in the middle, because there are many, many more ways for the heads and tails to end up in that proportion. There is only one way of getting 100 tails and no heads. Every single coin flip needs to go your way. But if you're looking for 50 tails and 50 heads, there are loads of different ways that the coin flips can go, and still give you that eventual outcome. So, what about 6 coins? We want to know how likely it is to get 3 tails when we flip a coin 6 times. Well, we can build up to this. Think about the first coin flip is either heads or tails. Well, in order to get 3 tails in 6 coins, then we're going to need either heads, 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 followed by tails, 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 or maybe heads, heads, tails, followed by something where tails occurs twice. There's various different combinations, but depending on what you've already got, that dictates what you need next. So for instance, here we are with 3 heads and 2 tails. We could still get 6 coin flips with 3 tails altogether. We just need the last one to be tails. So if we knew how many ways there were to get 2 tails out of 5 coin flips, then that would tell us how many ways there are to get 3 tails out of 6 coin flips ending with a tail. But similarly, if we'd got our 3 tails already in these first 5 coin flips, we would need the last coin to be heads. So if we knew how many ways there were to do that, that gives us the total number of ways altogether. Let's spell that out a bit more carefully. If we want 3 tails in 6 coin tosses, we either need to have already got our 3 tails in the first 5 coin tosses, and then we have to finish with a head, or we need to have got 2 tails in the first 5 coin tosses, and then of course we finish with a tail. If we can work out the total number of ways those two things can happen, we can just add them together. So how do we work those out? Well, luckily, the way we broke down the 3 tails and 6 throws can be broken down itself, so each of those terms can be written more simply. But it's a little verbose to write it out like this. So let's make up some notation. Instead of saying 6 throws giving us 3 tails, we're just going to write 6, 3 in a bracket. It looks a little bit like a fraction, and for reasons that we will come to later, we're going to refer to it as 6 choose 3, or n choose r. So we write it like this, and you can see it's a bit nicer to see what's going on. 6 choose 3, the number of ways of getting 3 tails in 6 coin tosses, is equivalent to 5 choose 3 plus 5 choose 2, the ways of getting 3 tails in 5 throws, plus the number of ways of getting 2 tails in 5 throws. Now, each of those we may not know the value of, but we can do the same thing we did with 6, 3. We can break it down further. So 5 choose 3 can be worked out by thinking about the first 4 coin tosses. You've either already got your 3 tails and the next one needs to be heads, or you've got 2 tails and 2 heads and you need the next one to be tails. Or for 5 choose 2, you can break it into 4 choose 2 plus 4 choose 1 in the same way. And remember, we've already worked those values out. We know what happens with 4 coin tosses. There are 4 ways of getting 3 tails. And there are 6 ways of getting 2 tails. That's the most common version. If you toss a coin 4 times and get 2 tails and 2 heads, there are 6 different combinations that have 2 tails and 2 heads. We do the same thing for 5 choose 2, and then we add those two things together. Now you can see all of those combinations written out for you here. You can see that on the green side, these 4 are the 4 ways of getting 3 tails within the first 4 coin tosses, and then we follow with a head, and then after that we need another head. Or we could have just 2 tails in the first 4 coin tosses, followed by a tail in the 5th coin toss, and then we have to finish with head to get a total of 3 tails on 6 coin tosses. Then on the right hand side with the orange, we've got a similar thing going on there. So you can pause if you want and check that those make sense. We can see how the situation with 6 coins is built up recursively from the situation with 5 coins, which itself is built from 4 coins, and you could keep going all the way down. We can just add them together, and we know that there must be 20 ways to get 3 tails in 6 throws, and then the probability follows from there. There are 64 different unique arrangements of heads and tails that you could get if you toss a coin 6 times, or if you toss 6 coins, because there are 2 different possibilities for each coin. So we've got 2 times 2 times 2 times 2 times 2 times 2. That iterative process can get rather confusing. It can mess with your head a little bit If you say, well, we only know about the 6 coin situation because we know about the 5 coin situation, and we only know those numbers because of the 4 coin situation, and so on and so on. If we build up from the ground upwards, things get a bit easier to make sense of. We start with the number 1, and from there we start to create a diagram that you might recognize. This diagram shows you what you saw when the turtles were moving through their random choices. There was only one way to be at the starting place. There was one way to move to the left once, and there's one way to move to the right once. There's only one way to reach that extreme bottom left corner, and there's only one way to reach the extreme right corner. But there are 2 different routes that will get you to the middle. You can see those 2 routes. You can either go to the left and then to the right, or alternatively you could go to the right and then to the left. Whereas if you're trying to get down to the extreme left, there's only one way to get there. Down to the extreme right, there's only one way to get there. But as we build up row by row, you find that these combine and build up, and especially near the middle, there are lots more options. There are 2 routes that will get you to that 2 in the middle, and therefore there are 3 routes that will get you to that 3, because there are 2 ways to get from the beginning to the 3 if we go via that 2, and there's one way to get from the beginning to the 3 if we go via this 1. So you can kind of see how these numbers are just showing you the number of different options, the number of different ways we can get from one place to another. And this method can be used to build up as many rows as you like. Turns out, if you go a bit further than our turtles went, if you go to 6 rows, you can see the 20 that we just calculated on the last slide. There are 20 ways to get to that spot, because there are 10 ways to get to the spot just before it on the left, and 10 ways to get to the spot just before it on the right. And we know there are 10 ways to get to those places because there's 4 and 6, or 6 and 4 ways respectively to get to the spaces before. So you can try this out for yourself. You can have a go at creating the routes. If you take some random zigzag, you'll find you can pretty easily find your way to the 20. But there's some fairly extreme routes that also get you to the 20. And if you try something in between, you'll find actually there's lots and lots of different ways you can get there. 20, in fact. Each number shows you how many different routes you can take to get to that spot, and we can use those numbers to build up and up and up. This is called Pascal's triangle. It has all sorts of useful properties, and you can build it for yourself. You'll get very adept and quick at drawing out at least the first few rows of this. You start with the number 1. You treat all blank empty spaces as if they were 0. In other words, that top 1 at the very top, we don't have 2 numbers to add together to get the numbers below, so we imagine it as being a 0 and a 1 and a 0, and then the zeros and the 1s can add together. So 1 and 0 give a 1. And then following that, anything along the edges is going to be 1, because there's only one way to get there. You have to go along the edge. But anything inside is going to be bigger, and the more inside you are, the bigger it gets. Turns out there are 70 ways of getting all the way down to a number like this one. That number also represents what happens if you toss a coin 8 times, and you want to know how many different ways there are of getting 4 tails. So we've looked at the 6 coin situation. How likely is it you get 3 tails? And it's 20 out of 64. Well, if you went all the way up to 8 tails, it would be 70 ways of getting 4 tails and 4 heads, but it will be 70 out of 256. And that brings me to the next interesting thing about Pascal's triangle. Every row adds up to a power of 2. 1, 2, 4, 8, 16, and so on. So we can see how it ties in nicely with their heads and tails situation. We also need to recognize that the best way of counting when we're looking at these rows is to use the same sort of indexing that a programming language like Python or Java would do, where the first element is known as the 0th element. So we have item number 0 at the very beginning, and then item 1 will be the second one in the list, and so on. The reason that makes sense here is that if you look along a row, the row we were looking at just down here with the 1 and the 8 and so on, we want to call that one row 8 because it has an 8 in it, and it has something to do with 8 coin tosses, and the numbers add up to 2 to the power 8, so we'd like to give it the label 8. And that's okay, as long as we recognize then that this one will be row 1, which means we're going to have to call this one row 0. Not only that, but the 8th row has, well, 1, 2, 3, 4, 5, 6, 7, 8, 9 elements in it. So that's another thing that's a little bit weird about it. But we can index those using a zero index method as well. We can call the very first number in that row the 0th element. So this is the 0th element, and that fits with what we were saying about 8 coin tosses. That is the number of ways to get 0 tails when you toss a coin 8 times. Here's the number of ways of getting 1 tail, number of ways of getting 2 tails, and so on, all the way up to the number of ways of getting 7 tails and the number of ways of getting 8 tails when you toss 8 coins. So we go from 0 both when we're counting which row we're on and when we're counting how far into the row we are. We also use this notation. In fact, this notation is the official formal notation that is used for this triangle. We talked about it as n choose r, and the reason we call it n choose r is that it represents the total number of ways of choosing r elements from a list of n items. So if you've got a class of 8 students and you want to choose 4 of them, there are 70 different ways to do that. A good way to think about how this links to the coin tosses thing is that if you have 6 coins that are going to be flipped and you're trying to figure out how many different ways you could get 3 tails, you could think of this in terms of, well, you have to have 3 tails and you have to have 3 heads. So the only question is, what positions do the tails end up in? Will they be in positions 2, 3, and 5? Are we going to have them in all at the beginning in positions 1, 2, and 3? Or maybe they're going to be in the even numbers positions 2, 4, and 6. You're choosing 3 numbers out of a collection of 6 numbers, and those 3 numbers that you choose, in whatever order you choose them, because the order doesn't matter, you're going to put the 3 tails in those positions. So that's how the choose connects to the number of tails we get. Notice here, again, this was our list of the 20 different combinations that give you 3 tails. That's the number 20. It's in row 6 and it is item number 3. 6 choose 3. And you can see how it comes from the green number 10 over here, which is 5 choose 3, and the orange number 10 here, which is 5 choose 2. The number of ways of choosing 2 items from 5 and the number of ways of choosing 3 items from 5, if you combine them, gives you the number of ways of choosing 3 items from 6. Now let's switch it up a bit and actually look at some binomial expressions. We're going to get stuck into a little bit of algebra and hopefully as a result get a glimpse at the underlying DNA behind this topic and the probability stuff we've been going on about so far. I'd like you to have a go at expanding all of these binomial brackets. Just do this in whatever current method you have. If you think you know something about binomial, try to leave that to one side for the time being and expand these out in the more traditional way. Think about what you would do if you know how to expand brackets, but you don't necessarily know anything more sophisticated about how to deal with higher powers. I'd like you to simplify your answers in full. So if you've got terms that can be collected, like plus x, I want you to turn it into plus 2x, and then write them in ascending powers of x. In other words, from the constant term, and then the x term, and then the x squared term, then the x cubed term, and so on. Just like this first example, 1 plus 2x plus x squared. I'd like you to answer all of these, but you might find it helpful to use your previous answer to work out a subsequent one. So if I asked you to work out 12 cubed, for instance, I'm guessing most of you would start by working out 12 squared and then make use of your answer to get to 12 cubed. Think about these in the same way and you might find that that's a slightly quicker approach. The other thing I'm hoping you'll do, if you get to the questions with stars next to them, if you think you've spotted a pattern, I'd like you to have a go at guessing what those expansions will be instead of having to work through them and calculate them longhand for yourselves. So pause the video, have a go at doing those 5 questions and see what you notice. Let's see what we have. For the first one, This one is just 1 plus 2x plus x squared. When we multiply out that pair of brackets, 1 plus x times 1 plus x, we get 1 times 1, that's the very first term from each bracket. We get x times x, that's the very last term from each bracket. And then we get the two middle terms. We get the 1 times the first, 1 from the first bracket multiplied by an x from the second bracket, and an x from the first bracket multiplied by a 1 from the second bracket. And overall that gives us the two x terms in the middle. If we then multiply that by 1 plus x, we get all of that, 1 plus 2x plus x squared, plus x lots of that, which will be x plus 2x squared plus x cubed. And if you put those all together, you get this. You can multiply those out in other orders in different ways as well. As long as you've multiplied every term by every term, when you're expanding brackets, you should get the same result. By the time you've done the third one here, hopefully you've spotted a pattern. You can see where this is going, and therefore you might well be able to guess, and hopefully you've managed to guess these two correctly as well. If you can't quite see where this is going yet, then take a look carefully at the way I've laid these out and think about where you've seen those numbers somewhere before. And you might find it instructive to calculate 1 plus x to the power 1. Of course, a power of 1 doesn't do anything. So 1 plus x to the power of 1 will just be the same as 1 plus x. And we could even go a step further and try 1 plus x to the power of 0. And no matter what the base might be, if you raise a number to the power of 0, we should get an answer of 1. So this was a number from Pascal's triangle that it's a little hard to make sense of. It's a bit more abstract perhaps than the lower rows. We can't think of it in very concrete terms when we're talking about tossing a number of coins and counting how many tails we get, because we're tossing 0 coins. But these numbers are Pascal's triangle, and we can see that top number as a power of a binomial. And in fact, if you look through, the only difference between Pascal's triangle and the expansions we see here are the powers of x. Every single coefficient, that is, every number in front of a power of x, all the coefficients of the powers of x are they're called the binomial coefficients, and they are exactly the numbers that appear in Pascal's triangle. That's a really important idea. That n choose r term, NCR, that tells you how big the coefficient of a power of x would be when you expand a bracket. So 1 plus x to the 6, if you expand it out, the x cubed term would have a coefficient of 20. This is the general formula, and it's beautiful. If you look carefully, you'll see it tells you how to expand any binomial with a positive integer power. 1 plus x to the power of 20, you just need to know what 20 choose 0 is, 20 choose 1, and so on. Now, some of those early terms are actually quite easy to calculate. N choose 0 is the number of ways of getting no tails when you toss a coin n times. And it actually doesn't matter what n is. The number of ways of getting no tails is only 1. There's exactly one way to do it. You get heads every time. That's the only way you can do it. Whereas n choose 1, the number of ways of getting one tail when you toss a coin n times, there are n ways to do that, because the single tail you get could be in any one of n positions. The other way of thinking of those is in terms of choosing. How many ways are there to choose one item from a collection of n items? There are n ways to do it. You just pick one item, there are n choices. Whereas n choose 0 is a little harder to get your head around, but how many ways are there to choose no items? Well, there's only one way to do that. You end up with nothing. Another way to think of it would be how many ways are there to choose all the items? That's the number at the far end, n choose n. And again, there's only one possible combination of all the items. It's every single item that you have. N choose n is the same as saying how many ways are there to get n tails when you toss a coin n times. There's only one way it can happen. Every single coin toss must be tails. So what is it about Pascal's triangle? Why does it connect in such a nice way to binomial expansions? Well, what we need to do for this is to look more closely at a particular example. Let's try 1 plus x to the power 4 and write it out as 4 separate binomial terms. 1 plus x times 1 plus x times 1 plus x times 1 plus x. And we're going to think about where the different terms come from. If we're expanding brackets, the rule is every single term gets multiplied by every single other term. When you expand a pair of brackets, this is true. That's why a pair of brackets where each bracket is a binomial will give you 4 terms in the final expansion, and then potentially we simplify after that. This has 2 terms in the first bracket, 2 terms in the next bracket, 2 terms in the next bracket, 2 terms in the next bracket. So overall, if you're going to multiply every possible combination, there's 2 times 2 times 2 times 2. That's 2 to the 4. That's 16 different things that you can get. Maybe you do 1 times 1 times x times 1. Maybe you do 1 times x times x times x. There are 16 of those different combinations, but some of them give you the same result. So see if you can answer these questions. Where will the x to the 4 term come from? If you're expanding these brackets and you're choosing a term from each bracket to multiply, which terms do you choose that will multiply together to give you an x to the 4? And then what about the x cubed term? Where does that one come from? And then finally, how many different ways can you choose a term from each bracket in order to generate an x squared term when you multiply them? Have a think about those questions. See if you can write them down. Perhaps see if you can expand out 1 plus x to the 4 by thinking of it in terms of 4 separate binomial brackets, and see physically where all the different combinations of numbers come from. Pause at this point and try to answer those questions, and then we'll talk through them together. So for the first one, the x to the 4 term, there's only one way you can generate that. To get the x to the 4 term, you pick an x in the first bracket, an x in the second bracket, an x from the third bracket, and an x from the fourth bracket, and you multiply them all together. But for an x cubed term, you've got a lot more choice. There are 4 different ways you can do this. You need 3 x terms and a 1. So we could choose to have the 1 come from the first bracket, or from the second, or the third, or the fourth. There's 4 different ways that can happen. And then what about an x squared term? This one, there are 6 ways to do it. We need 2 x's and 2 1's, but they can come from any of the brackets. And we've already seen how there are 6 different ways to choose 2 things from a collection of 4, or to allocate 2 positions from 4 possible positions, or to get 2 tails when you toss a coin 4 times. They're all really the same question behind the scenes. So we say there's 4 choose 2, or 6 different ways to make the x squared term. You can see a few of them here. Maybe we've taken an x from the first and last bracket and a 1 from the other 2. Perhaps we've decided that the first and third brackets need to give us an x, and we're going to take a 1 from the second and fourth. Or even the middle terms have x's and the first and the last have 1's. There are, like we say, in total 6 different combinations we can do like that. Now we're going to look at an extended version of that formula that we've already seen. So we've already looked at 1 plus x to the power n, and that's all very well, but most of the binomials we deal with are probably not going to be 1 plus x to the power of something. They'll be something else plus something else, 3 minus 7x to the power of 5, or a half minus a quarter x squared to the power of 19. Whatever they might be, if they are binomials, if they are 2-term expressions, we can apply this formula. We just need a slightly different variation on it. So we need to think in terms of the powers of a as well as the powers of b. You remember the examples we just talked about, we've had powers of x and powers of 1, but of course powers of 1 are all just 1, which makes things a bit simpler. When we've got powers of a as well as powers of b, we need to think of 3 different things all at the same time. I've tried to color code them because this does look messy. But if we had, let's say, 2 plus x to the power 5, there are 3 different aspects to this that we need to look at. One of them is the binomial coefficients. They're the bits in blue. 5 choose 0, 5 choose 1, all the way up to 5 choose 5. Those numbers are exactly the 5th row from Pascal's triangle. So 1, 5, 10, 10, 5, 1. And you can generate them for yourself very quickly just by jotting down the first few rows of Pascal's triangle when you first start a question like this, or you can generate them from your calculator using the NCR button. 5 NCR 2 will tell you that there are 10 ways of choosing two things from 5, and it will also give you the binomial coefficient that belongs with the x squared term. Now if you look at the green bits, those are descending powers of the first nomial, the first number in the bracket. So we've got powers of 2 that go down from 2 to the 5 all the way down to 2 to the 0. And at the same time, we've got a corresponding ascending powers of x to the 0 all the way up to x to the 5. And I've shown it in this form, in this unsimplified form, so that you can see where all the pieces come from and the pattern behind it, so that you could easily convert this. If x became y, or if 2 became x squared, you could replace that term and you could apply the same logic with the powers, ascending or descending powers, with those binomial coefficients. The other thing, if you're wondering why 2 plus x instead of x plus 2, there's no good reason for that. It doesn't matter which way around they go. X add 2 is of course identical to 2 plus x. So we could have ascending powers of 2 and descending powers of x if we liked. The reason it doesn't matter is that the binomial coefficients are also symmetrical. The entirety of Pascal's triangle has symmetry. So 5 choose 5 is the same as 5 choose 0. They're both just 1. And 5 choose 4 and 5 choose 1 are the same. They're both just 5. Because there's the same number of ways of choosing 4 things from 5 as there are of choosing 1 thing from 5. If you look at the fingers and thumb on your hand, you've got 5 digits on your hand. And if I said pick one, well, you point to one of your fingers or your thumb. The act of choosing one of them is mathematically equivalent to the act of choosing which ones not to point at. So if you're pointing at one of your fingers or thumb, then you're not pointing at the other 4. So choosing 1 thing from 5, choosing 4 things from 5, the only difference is your perspective. So there's the same number of ways to do it. If you pick 4 things, you are picking everything except one of them. Now there's a nicer way to write this, of course. If those blue numbers are all just the binomial coefficients from Pascal's triangle, we can replace them with 1, 5, 10, 10, 5, 1. The powers of 2 can also be simplified. And the other thing I'm going to do is the x's. X to the 4 and x to the 5 will look exactly the same, as will x cubed and x squared. But we don't normally write x to the power 1, we write x. And x to the 0 is just 1, so that one doesn't need to be written at all, because if you multiply by 1, it doesn't change things. So this immediately looks a lot nicer. I've simplified the way I'm writing the powers of x, and I've simplified the binomial coefficients. The next step is to sort out those powers of 2, and to multiply them by the respective binomial coefficients. 32 add 80x, add 80x squared, add 40x cubed, add 10x to the 4, add x to the 5. It's lost some of that symmetry that we saw in the original binomial coefficients because the 2 and the x don't have the same sort of symmetry as 1 and 1x do. But we now have a way of applying the same underlying methodology to any binomial. This, incidentally, is provided in the formula book. And you can see it looks a little confusing because it's all algebra. There's an A and a B and an N, and then there's an R kicking around later on. But this is just a general way of saying exactly what we've just done. We use 2 and x. Here they're using A and B, so you can see you can replace A and B with whatever you like. And if you look carefully at the powers of A, you'll see that it starts with A to the N, and then goes down 1 to A to the N minus 1. That's equivalent to saying, well, if you want a power of 5, you start with A to the 5, and then you have A to the 4, then A to the 3, and then A squared, and so on. And you keep going down, following the same pattern, so that the power of A and the power of B always add up to n. When we had 2 to the 4, we had x to the 1. When it was 2 cubed, it was x squared. 2 squared, x cubed. The powers both have to add up to 5, because if you think about it, we've got 5 brackets, 5 identical brackets all lined up, and we're picking either a 2 or a 5 from each bracket. So at the end, we'll have 5 things, some of them 2's, some of them x's. And when we put them all together, we'll have some power of 2 and some power of x, but the powers have to add up to 5. Nice thing to think about here. If you expand h add t to the power of 5 using this formula, then we can directly compare the algebraic expansion that we're looking at here with the probability situation we were talking about earlier. If we represent the probability of getting heads on a coin toss with H and the probability of getting tails with T, well, one thing we know for sure is that H plus T must be 1. Even if we have a biased coin, the probability of getting heads and the probability of getting tails must add up to give 1, because those events are both mutually exclusive and they're mutually exhaustive. Mutually exclusive means they can't both happen at the same time. There's no possible way of getting heads and tails on the same coin toss. Mutually exhaustive means that one of them at least must happen. There's nothing else that can happen. If you didn't get heads, you got tails. If you didn't get tails, you got heads. So exactly one of these events will happen, and that means the two probabilities add up to 1. But that means h add t is 1, so we've got 1 to the power 5, and h add t to the power 5 must be 1. But then you can expand with binomial and turn it into a bunch of different terms. And if you try that, if you expand out h add t to the power 5, each of the different terms gives you the probability of getting the corresponding number of heads and tails. It's worth having a look at that, trying to expand it out, have a think about it, maybe ask me about it later and we can go through it in a little bit more detail. Perhaps we can see how it works for biased coin tosses. And it's the essence of the binomial probability distribution that you're going to be making use of later on in statistics as well. Now let's try a question. We're going to dive straight into quite a complicated looking question so that you can see how this technique tends to be applied. This one is telling you the size of the x squared coefficient in the particular expansion, and you're being asked to work out the possible values of the constant b. So they're making this harder by making you work backwards. 3 plus bx to the power 3 is something that we need to expand and can most easily be done using the binomial expansion formula. But our expansion is going to involve b because we don't know the value of b. Once we've done that, we need to multiply by 2 minus x. And that's going to give us something which is not just cubic but actually quartic, because we're multiplying something linear by something cubic. And then we've got to look at the x squared coefficient. Now, the first thing we're going to want to do is expand that cubed term. And we can do that by identifying the binomial coefficients, 1, 3, 3, 1, by using descending powers of one of the nomials. So I'm using 3 cubed, 3 squared, 3 to the 1, which is 3, and 3 to the 0, which is 1. And then ascending powers of the second nomial, which is bx. And you'll notice that I'm putting bx in a bracket, so that when I get to bx squared, that's the entirety of that second term being squared, which means b gets squared as well as x. We can simplify that, and this is what we get. And you'll see that because we don't know the value of b, we're still stuck with b kicking around within our expression. Now, this bit gets clever. We do need to multiply by the bracket 2 minus x, but all we care about is the x squared term. So we don't need to work out the entirety of this thing. There are 4 terms in the expansion of 3 plus bx cubed, and if we need to multiply them by 2 minus x, we're going to end up with 8 terms. But we don't care about all 8 of those terms. So I've grayed out the 27 and the b cubed x cubed because they're not relevant for us. We can't get an x squared term by multiplying 27 by anything in that first bracket, because 27 is only a constant. The most it can give us is a minus 27x if we multiply it by the minus x term. Similarly, the x cubed term in our expansion of the cubic, that's not relevant to us either, because it's too high a power of x to give us an x squared term. But if we were to multiply 2 by 9b squared x squared, that would give us an x squared term. It's not the only way to get one though. We can also multiply negative x by 27bx, and that gives us another x squared term. That's the only way an x squared term can come. It's going to come from a constant times an x squared, or an x times an x. Once we've got that, we can make use of the fact that the question tells us that the coefficient of x squared is 45. Well, we know the coefficient of x squared is minus 27b add 18b squared. So we turn it into an equation, we rearrange a little bit, and to be honest, we'd probably let the calculator do the hard work for us here. Remember, the class width will let you solve quadratics without you having to do all the factorizing or even using the formula for yourself. It'll do that work for you. And we get two relatively nice numbers, 2.5 and -1. Now you should be able to have a go at a few questions. I've picked out a few from exercise 8a that you can dive into straight away. Get a bit of practice doing the straightforward binomial expansion. They'll give you a bracket with a power. You try applying the formula and simplifying. Be careful with your calculator, make use of it, but watch out for the terms that you're squaring or cubing. If they're not just x, if they're something like 3x or -x, put that in a bracket so that you're squaring the whole of 3x or you're squaring the whole of -x whenever you have the square of x in the formula. The last thing we've got on binomial expansion is an exam question for you to have a go at. This one's a classic. It involves quite a large power, which means you're probably going to rely on your calculator for the n choose r binomial coefficients. But because they don't expect you to waste ages calculating all 9 terms of the expansion, they're only asking for the first few. They do a similar thing to what we've just seen in the second part of the question, multiplying your expansion by some other bracket. There's a couple more things you're going to need. You'll need to look in the formula book, or I'll include it on the screen here. This is the formula for binomial series from your formula book, and it includes this little extra bit where NCR equals this. A couple of different ways of writing the notation, and then this crazy little formula, n factorial over r factorial n minus r factorial. This is the number of ways to choose r items from n. That's what we were talking about before. And we can say this as NCR or n choose r. And this refers to the factorial function. So once you've had a go at this exam question and I've talked through the solutions, there is a bonus section to this video where I go into a bit more detail of why the NCR formula is what it is and what on earth it has to do with factorials. So pause the video, have a go at this question, and then come back for the next little section where I go through the answers, and then if you're able to, stick around for the bonus section. Right, we're going to go through the answers to this question now. At the beginning, if we expand this out, we can make use of the formula. I'm writing 8 choose 1 and 8 choose 2 and 8 choose 3 for the binomial coefficients. And then because it's a 1, we don't need to worry about the descending powers of the first nomial. They're just all going to be 1, 1 to the 8, 1 to the 7, and so on. So we just need ascending powers of the x term, which in this case is 2x. So 2x in a bracket, 2x squared, 2x cubed, and so on. Now, at the end of this line, I've evaluated the binomial coefficients. To complete the question, I also need to sort out the powers of 2x. So 2x in a bracket squared is 4x squared, and so on. At the end, this should simplify to give me this. And then I can read off the values of a, b, and c, which is what they've asked for in the question. For part b, we can make use of the expansion we found in part a, and I just need to multiply that entire thing by 1 plus a half x. Remember, if you're multiplying brackets, all we need to do is multiply every term in each bracket by every term in the other bracket. Now we've got 2 terms in the first bracket and 4 terms in the second bracket, which will give a total of 8 altogether here, even if we only use the ones we've got. We've put plus ... because the expansion continues and we've only given the first little bit of it. But we don't actually need to look at all 8 terms because we only care about the coefficient of x cubed. So we've got to ask ourselves, where does the x cubed term come from? Well, there's only a couple of places it can come from. A constant multiplied by an x cubed term and an x term multiplied by an x squared term. So that's how we finish. We can do the 1 times the 448x cubed, or we do the half x multiplied by the 112x squared. Those combine to give us 504x cubed, so the coefficient of x cubed is 504. Now you should be able to have a go at a few more advanced questions. You can look at exercise 8b. Questions 5, 6, and 7 are quite good ones to try. Welcome to the bonus section. This is where we're going to look at the n choose r formula a little more carefully and see perhaps a bit of why it involves the factorial function at all. To do this, we're going to return to the question we previously answered. If I flip 6 coins, what's the chance of getting 3 tails? but we're going to look at it from a slightly different direction. We want to ask the related question, in how many ways can we choose 3 items from a collection of 6 items? And you might remember we talked about the elements of Pascal's triangle representing the binomial coefficients, the n choose r or NCR numbers, and we said these are the numbers that represent the number of ways to choose r items from 6. The crazy formula that you've got in the formula book involving factorials is the formula for NCR, and we're going to try to find out why. But first we need to get it clear in our heads that the question about coin flips is essentially the same question as the question about choosing 3 items from 6. If we're trying to find out how many different ways there are to get 3 tails when you flip a coin 6 times, that's effectively the same as saying I've got 3 tails and 3 heads and I want to shuffle them around. I want to move them into different places. So really the question is, which 3 positions will the tails be in? Will they be in positions 1, 4 and 6, or will they be in positions 1, 3 and 5? And how many different ways are there for them to be in 3 positions? We're basically saying, imagine you've got a deck of cards and there are 6 cards, just 6, and they're all numbered differently with numbers 1, 2, 3, 4, 5 and 6, and you're going to shuffle them up and then deal 3 cards. You're going to pick up your cards. The order that you get dealt the cards in doesn't matter. So we're asking how many different 3-card hands could you make? You might get a 1 and a 2 and a 3. Possibly in that order, possibly a different order. You might be given the 2 first, then the 1, then the 3. That's not what matters. What matters is what are the 3 numbers that come out, because those 3 numbers will determine, in the context of our problem, which coin tosses came up tails. So let's start with this. This is every single possible ordering of your 6 cards. Now, if we tried to do this with 52 cards, we'd need a slightly smaller font. But with 6 cards, we can just about manage it on the screen. We've got all the cards in perfect order, 1, 2, 3, 4, 5, 6 at the top left, and all the cards in perfect reverse order, 6, 5, 4, 3, 2, 1 on the bottom right. And you might have to take my word for it, but all the others are in there as well. I believe these are in ascending order if you read them as 6-digit numbers, but think of them in terms of 6 individual items in every single possible shuffling order you can have. And the first question is, how many are there? You might want to have a think about that before I reveal the next answer. How many different ways are there to shuffle a deck of 6 cards, get a different result? I recommend you don't count them, but you see if you can find an efficient way of answering the question. Pause if you need to, have a quick look at that table and see if you can work out anything about what's going on. What we should have is this, 6 factorial. The factorial notation is just a way of saying I want to multiply this positive integer by every positive integer below it until we get down to 1. 6 times 5 times 4 times 3 times 2 times 1. And the reason for that is that if you are putting your 6 cards in order, you can pick any one of those 6 to be the very first card in the deck. But then once you've chosen one of those 6, there are only 5 choices for the next card that you put down. And after those 2 cards have been put down, there are only 4 choices for which card comes next. And the number of choices reduces every time until by the time you get to the last card, if you've already decided what the first 5 cards are, there's no more choice for the last one, or you could argue there's a single choice. There is one possibility for the card you put down at the end. So your final card is a forced choice. And we have a total of 720 different ways of shuffling those 6 cards. And that's the ones that you can see on the screen in front of you. Now, I want to zoom in on this bit so you can see the numbers a bit more clearly. And I'd like you to look for a particular result. Because remember, all we care about is the first 3 cards. We're imagining shuffling this deck of cards and then dealing ourselves 3 cards. So it's just the first 3 digits that we're interested in. And we've got a slight problem here. We've massively overcounted. We're looking at every single possible way of shuffling the deck, but quite a lot of those different ways of shuffling the deck give us the same 3 cards at the beginning. So for instance, can you find any arrangements that have the cards 2, 3, and 6 at the beginning. Now look carefully. I want you to see if you can find all the possible arrangements with a 2 and a 3 and a 6. They can be in any order. You don't have to be dealt the 2 and then the 3 and then the 6. You might get the 6 first. You might get the 3 and then the 2. You might get the 3, then the 6, then the 2. There's lots of ways that can happen. The other 3 cards will be in the final position. The 2 and the 3 and the 6 need to be at the beginning. See if you can find all instances of those on the screen. All right, here's the first one I found. 2, 3, 6, 1, 4, 5. So the 2, the 3, and the 6 are in order, and then the 1 and the 4 and the 5 that come after them are also in order amongst themselves. But that's not the only time that we get 2, 3, and 6 at the beginning. In fact, if you look just below, there's 2, 3, 6, 1, 5, 4. Well, the 1, 5, 4, they're just the cards that got left in the deck after we dealt out the 2, the 3, and the 6. So that's not going to feel any different to us. In fact, from the coins perspective, I'm saying I need to get tails on the second coin toss, the third coin toss, and the sixth coin toss. And that's equivalent to all of these, getting tails on the second, the third, and the sixth. But that's, again, not enough. Look at these ones. 2, 6, and 3 is the same as 2, 3, and 6. So we've not just overcounted because of the different orders in which the remaining cards could go, but we've overcounted because of the different orders in which the 3 cards we pick out could come. There's more and more. In fact, these are the ones that either start with a 2 or start with a 3. We've also got the ones that start with a 6, 6, 2, 3 something, and way down here 6, 3, 2 something. There are 6 blocks, and each block has 6 numbers in. So we've overcounted by a factor of 6 because of the order of the first 3 cards. We basically don't care what order the first 3 cards are in. So each of these 6 green blocks is equivalent to each other green block. But also we've overcounted by another factor of 6 because within each green block, all the results are equivalent again. And it's not just this particular set of green blocks that's special. Any number you pick from this list of 720 will be equivalent to another 35 numbers. There'll be 36 different entries in this massive table, which for our purposes are equivalent. If you pick an entry that says, for instance, 461352, then there'll be a bunch of other entries that are equivalent, like 461325 and 416352, and so on and so forth. There'll be 36 of them, so we've basically overcounted by a factor of 36. And that means that we can get the exact value that we need by dividing by 36. We start with 6 factorial, which is the total number of ways of arranging n items. We divide by 3 factorial to adjust for the number of ways of arranging the ones we're going to choose. And we also divide by 3 factorial because that's the number of ways of arranging the 3 that we're not going to choose. That's where the n factorial, the r factorial, and the n minus r factorial terms come from.